Hey guys, welcome to Introduction to Python for Data Science. I'm going to be talking about a couple of topics, variables and assignment statements, basic calculations, single quoted strings, input from users, and then control statements. And then we're going to move on to functions, lists, tuples, sets, and dictionaries, and strings. And then finally, object-oriented programming, NumPy, pandas, data visualization, statistics, and machine learning. So this basically covers all the topics that are in data science. Um, they're going to be the basics, though. They're not going to be going too much in depth. So let's start. So first, we're going to start off with variable and assignment statements. Basically, just basically simple addition. You could see this 190. I did that. I mean, I could try something else. 10 plus 200, 210. Okay. And then we could assign these variables assign these numbers to variables. Okay, so if x is equal to 7, y is equal to 10.1, I could save that. And I run something like this, I'll get 17.1. Now, we could also kind of ask the question what type of variable it is. It could be either something called an integer or a float. An integer being like a whole number, like a 7, and then a float being something with a decimal place. So we get int and float, okay? Now we move on to some basic calculations, multiplication, 9 times 8, 72, taking the power to something. We've got this double asterisk. 5 to the second power is 25. We want to get the square root of 25. We would do the same thing, but we would use 0.5 here, right, for a half. Now, basic division, we just use this slash, and then we get 10 divided by 3 is 3.3. Here, we just get to the whole number, right? So this cuts off, this decimal place cuts off. It's like how many times does 10 go into, how many times does 3 go into 10? 4 divided by 5 is 0.8. 4 divided by 5 with the double slash, it discards the fractional part, right? So it's going to be a 0. Negative 15 divided by 2 is negative 7.5. And then what is not greater than negative 7.5? Right? It's going to be negative 8. That's what this double sign does. The remainder is the percentage sign. So 2 goes into 15 7 times, right? But then there's a remainder of 1. Okay. Um, Here I'm going to give you kind of the importance of parentheses. These are like mathematical operations that we learned, I think, in high school. But in any case, we run this. It's the multiplication always goes first, right? So 20 times 10 plus 2. I mean, it wouldn't matter 302. So it's always the multiplication that goes first before the addition. Here we want to do the calculations in the parentheses before we do the multiplication, right? So it's 10 plus 2, which is 12 times 20, which is 240. Here I give a brief table giving the precedence in terms of what's the most important in terms of order. So parentheses obviously is the most important. Exponentiation is the second. The division, multiplication, division, floor division, modulus would be the third, and then addition and subtraction would be the fourth. So here we do 2 to the second power, which is 4, times 1 plus 5, which is 9. So it should be going from left to right as well, right? So that's another important point to make is that the multiplication should go first, and then the addition second. Okay, so from left to right, we're doing this from left to right. Here we've got we would do this first, right? Um, parentheses, which is 6, then the exponentiation, 2 to the second power is 4, and then finally the multiplication, which is 4 times 6, which is 24. Here we're going to go on to single, double, and triple quoted strings. Not really a big deal. Just basically single quotes in this print statement will give you Python is awesome. I mean, the same thing will occur with the double quotes. If we want to separate the strings, we could print that out and it'll string together. Similar results to the two below, okay? Now, if we wanted to embed quotes within a string, we could do so by using first the single quotes on the outside and then the double quotes on the inside. I mean, these print statements, the reason why we would do something like this, I mean, is to kind of give more emphasis maybe to a word, right? I mean, that's one of the reasons that you could use that. Now, if you want to print out a variable, you can do so by embedding just the variable number in this print statement, right? I mean, first you have to put the string and then a comma and then the variable number. And you get x is the number 5. Here we go on to using something called inputs from users, right? So, I mean, we see this in everyday applications like a password, for example. So if I run this with this input statement, I mean, I'm going to do something like 1, 2, 3, 4, 5. I mean, that's obviously a bad password. And then I hit enter. Oh, wait, so what happened? Yeah, okay, let me try this again. Yeah, so it's 1, 2, 3. I mean, not a big deal, okay? If I run the password, 1, 2, 3. And it'll come out in a string. That's an important note, okay? So it's like it doesn't emphasize like any number, right? So it's going to be like ends up being a string. We'll see what we can do later on with that. I mean, we're going to use an int just to fast forward a bit. But here, okay, let's say enter a number. Number 7, enter another number. It's 8. Now we add these two, 78, okay? Notice it's not 15, right? Because we're actually concatenating two strings. So we're putting the 7 and the 8 together, and that's the string, okay? Now this example, as I was mentioning earlier, will actually input real numbers, okay? So if I put in the number 56, we'll get that. And then we could check that, okay, by using the type that we saw earlier, and that's an integer, okay? So if I did something like I added this 7, 8, if I was to do it, it would end up being 15 versus 78, right? If I did this, if I did a number 1, number 2, enter two numbers, it would end up being a 56. I mean, a 15 instead of a 78. Here we go on to using some control statements and comparison operators to make decisions in the program. So if 10 is greater than 15, it'd be false. 10 is less than 15 is true. These Boolean operators are actually very useful. I mean, you'll see later on that Boolean expressions could be, used as true, false, 0, 1, or whatnot. It's useful to kind of indicate whether something is or it isn't, okay? There's other comparative operators, right? If x equals to y, if it's not equal to, greater than or equal to, we just saw that, greater than or equal to, x is not, x in, x not in. These are all Boolean operations, okay? It's either true or false. We're going to quickly move on to if statements. So like an if statement is basically we start with initializing a statement. We check the condition. If it's true, it runs. If it's false, it exits. Here's an example. So number 1 is equal to 2, number 2 is equal to 2, 2 is equal to 2. Okay, so this is true, right? So that the statement will execute, right? So what if I put a 3? 3 is not equal to 2. Okay, so this is a not equal to. So this part of the code will not execute because it's not equal, right? But this part will, because they are not equal. Okay. What if we were to ask whether a number is odd or even? If I put a 2, obviously that's an even number. Even, finished with conditional. Let's try again. 3. Okay, something broke here. Because I interrupted it. We'll try 5 this time. Yeah, odd. Okay. Recall that for an even number, the remainder has to be 0. Okay. And you're dividing it by 2, right? So if it's 6 divided by 2, it's equal to 3. There's no remainder. If it's 5 divided by 2, 2 will go into 5 2 times, but there will be a remainder of 1. So that's what makes it odd. In an if-else statement, there's more choices that you can make. So basically, you could start if condition, body of if it happens to be true on the first shot, it ends. If it's false, it'll go on to another condition. If it's true, it'll end up ending. If it's false, it'll have to go all the way to the end of the program, which is the else statement, and then it'll end here. So that's a brief description of the process that occurs within an if-else statement. Now, a concrete example, if I was to say, let's enter a grade and see what kind of grade we get. I mean, looking at the logic here, we see the LF, LF, and then finally, if they can't make past 65, then they'll fail, okay? So it's pretty much easy goings if it's like a 95, right? It'll hit the first condition and then basically it'll exit the conditional statement. Now, what if I put 75? It'll bypass these, and then it'll go to this, okay? Finally, if I go to 50, it won't meet any of these 4 conditions. They'll have to go to else. And then basically the person failed the test. Here I'm going to be talking about a nested if statement. So if I say 7, right? It's not divisible by 2 or 3. Okay, so if this is even, right? And if this is equal to 0, right? If it's divisible by 2 and divisible by 3, right? Then it'll print divisible by 2 and 3. If it's not, it'll present, if it's divisible by 2, but it's not divisible by 3, it'll print this. So let me try this again. And we know that 6 is divisible by 2 and 3. So if I print 6 and then run this again, this nested if, it's divisible by 2 and 3. Right? What if I said 3? It's divisible by 3, but not by 2, because 3 divided by 3 is equal to 0, obviously, but it's not divisible by 2. Okay. So that's an example of a nested if-else statement, something like an if statement within an if statement. Okay. Now we're going to move on to a while loop. So say, for example, you wanted to print y x amount, some amount of times, right? So it's like number of y is equal to 1. We do y, 2, 3, but we wanted to kind of go forever. And you could see kind of by looking at this, it's almost like an impossible task where you have to constantly just put the numbers and the numbers and so forth. There's a way to solve this problem, and we could use something called the while loop, where we test these conditions, and if it's true, it'll execute the condition, but if it's false, it'll exit it, right? So it could go on forever, right? We could put in the number of times, like how many times you want to print y. Okay, let's try this. Now, if I said 10, it'll print it 10 times. 3, 4, 5, 6, 7, 8, 9, 10. Okay. So remember, from a string, we could concatenate it, right? And we start off with this to print an empty string, and then we count each time we want to add, right? So the counter here is 0, but we start off with 1, then we count to 2, then we count to all the way up to how many times we input it. So like let's start off with like a smaller one, 3. What we would do is we would start off with 0. 0 is less than 3. We're adding 1, then it would go 1 is less than 2. And then we would add another one, it would go 2 is less than 3. And then it would stop. It would stop when this hits 3 because it won't be less than 3, right? So that's the idea. The while loop is actually helpful because, as I was mentioning earlier, we don't have to go through all this coding wise. So that's why the while loop is actually helpful. Now, the while loop is executing until a particular condition is met, right? And then it stops. Here in the for loop, we could actually specify the condition. So that's a difference between the for loop and the while loop. Now, let's try this out. How many iterations do you want? I would say 20. And it would go in and it would go from 19 because it counts from 0. Range starts with a 0 to 19, okay? Now, we saw that we specified the condition, but here in the while loop, it's when the condition is met or it fails is when it exits the loop, okay? So when the condition fails, that's when it exits it. Here we specify the conditions. Here's another simple loop. Basically, every loop starts with initializing something. So it's like here is an empty list, okay? And then from range from 0 to 5, or it starts with 0, it goes to 4. We append each number to this particular list. And we're going to be going into lists a little bit deeper later on. But if I run this, it's 0 to 4. So remember, this number specifies it's not included. It's every number included but 6. So 0, 1, 2, 3, 4, 5, where it starts at 0. Now here's a double for loop, getting a little bit more complicated, but we have an I in range X and a J in range X, okay? So I just say 2, we'll see this. And this is the outer loop, right, which is the I, and the J specifies the inner loop. And I specify 2 iterations, so there's 2 iterations for each loop. There's 2 outer loops and 2 inner loops for each outer loop. Now moving on to using enumerate, we could initialize a list, which is denoted by these brackets, and it's called fruits, okay? And then we saw the range from 3, it would go 0, 1, 2, okay? And I would append a fruit each time, okay? So let's try something like this. And I put the input statement within the loop, if you notice. So I go apple, orange, pineapple. Right? Here in the enumerate, what I did was I enumerated that list, okay? From apple, orange, and pineapple, okay? So what this did was this appended each time after each iteration, right? So it went apple first, then the next iteration, it would go to orange, then it went to banana. I'm sorry, pineapple, right? And then from this new list here that this loop created, this enumerate for loop, it would collect the index, the item, right, in enumerate fruits. And then it would print out the index and then the item. So index, like I was mentioning, the range is 0, 1, 2. It goes 0, 1, 2, apple, orange, pineapple. But that's exactly what it did behind the scenes. Okay. Hey guys, so we're going to be moving on to functions. Functions are useful in data science because they promote code reusability, readability, and maintainability. They help automate repetitive tasks like data cleaning or modeling, saving time and reducing errors. Functions also simplify debugging and collaboration by isolating specific tasks. So there's a lot of truth to that statement. It's actually pretty well known among data scientists that you're going to have to use certain things over and over again. And instead of like running or rewriting blocks of code, you could capture all of that information in a function and then apply it to data or models or whatnot. Here we're going to give just a simple example, but I mean like the square root, for example, we could use this square root num, right? This is the variable, the parameter, and it's going to return this num to the square root of 0.5, okay? Now, instead of, I mean, like if we would have to do this over and over again, for example, we don't want to do 2 to the square root, 3 to the square root. I mean, we could just call this square root function and then put whatever number in and do that. Okay, so square root to the 25 is 5, obviously. Oops, I got to run this first. This, we get 5. Now, functions could also have multiple values. Oops. That's the problem with that. Okay. We can multiply 2 times 3, which is 6. Here's a little tip in programming in Python. It's always nice to write something called docstring, use something called docstrings, especially when you're working with people. If you have a function, you kind of give them a brief overview of what it does, right? And maybe the parameters, if it's an integer or float. I mean, this is just a quick example. It's good coding practice. It's also being considerate to people that are using your code. So it's a useful thing to know. There's functions also with default parameters values, right? Where you specify it already and it just runs. Here I do 2 times 3, run this, and I just run this code, I get 6. It's important to note that the assignment, it's assigned left to right. So this 10 here, it would override the 2. Okay, so if I was to run that, it would be 30. So lists and tuples are important in data science because they efficiently store and organize data. Lists are mutable, which means changeable, and it allows for easier modification, right? While tuples are immutable, and they provide a stable structure for data that shouldn't change. Okay, so both are essential for handling collections of data, such as features in a data set, model parameters, and intermediate results. And you'll see that later on when you deal more with machine learning models. Like you're going to have to go a little bit deeper into it, deeper than what we're going to be covering here. But for that being said, here's the first list, and we could see that basically it's a list of integers and a float, and we run it, pretty much stores the data. We could also combine strings and integers and floats, right? So it's really agnostic in terms of what kind of data you put in it. We could access the first element of a list by indexing it to 0. Now remember, this is 0, 1, 2, 3, 4, 5. So that's how it would go. If you recall earlier in the range, when we looked at the for loops in the range, it always starts at 0. The index always starts at 0. Same thing with B. I mean, we got Python here, B3, R. And just to check, we could count again, 0, 1, 2, 3, which is R. Lists are mutable, like I was mentioning earlier, it's changeable. So like if we want to replace 0, 1, 2, 3, R with Python, we can do so with scikit-learn, we could do so. So we do that. And I've already previously run this. So scikit-learn replaces R. Now we could also concatenate lists, which is basically adding these two lists together. Notice that it's just basically element by element. It's adding element by element. Here, I'm going to do some methods with the list. Now, this is a simple list. We've seen append previously in the for loop, but if I want to append a 9, we get this. 3, 1, 4, 1, 5, 9, which is the last element. Now, if I wanted to add multiple elements, I could use this extend statement. And you could see this is a list of 2 and 6. And by running it, we add a 2 and 6 to the end. Now, if I want to insert an element at a specific position, I could insert the 7 at index 2. Okay, so it's 0, 1, 2. Right now, 4 occupies the index at 2, but we're going to replace that with the 7. And when we do that, it becomes here, and we push back the 4. Now we could remove the value 4 from the list. So this has to match something in the list. If it's not in the list, it won't remove it. So it's like I'll run it with a 4, it removes the 4. If I want to remove 6 at the end, the 6 disappears. This also removes it removes an element from the index. And let's see what it does. So it removed the 2. Okay, so it pops. What it does is it removes the last element in the list. So the 9 disappears, the 5, the 1, the 7, the 1. Now we're with 3. Now it's empty. So that's the idea of pop. Now that I've gotten rid of all of the, okay, yeah, so I think I have my original list. So I could still sort it. So my list sort, oh, yeah, right. It didn't. Okay, so I have to rerun this. Let me rerun this. My list. And you see it's out of order. There's 3, 1, 4. Let's see what it does. Obviously, you should pretty much know what a sort does. It sorts it. 1, 1, 3, 4, 5. Yeah, here. There's also something called two-dimensional lists. You could see here, we have a list within a list, two lists within a list, okay? So if I run this, and here's kind of the breakdown of what it is. Row 0, column 0 is A00, which basically is this value, 0. If I go row 0, column 1, it's 1. If I go row 1, well, let's see it. Let's break it down anyway. I might make a mistake. So let's just run this. A00 is 0. A01. Okay, so I think I was saying it. Yeah. A0, yeah. So A0 is 1, okay? Now let's do more of it just to make sure that we're on track here. A10 should be 2. Yep. Now we add it again. A11 should be 3. Okay. So now let's look at another two-dimensional list with 3 rows and 4 columns. Now the rows are designated by the lists. We've got 3 lists within a list, right? So we've got 1, 2, 3, right? So each list is considered a row, and each number in the list is considered a column. So I do the same thing here, A00, column 00, column 01, column 02, column 03. So this is 0, this whole list. And then each of these elements within the list are indexed by a column 0, 1, 2, 3. 0, 1, 2, 3, 0, 1, 2, 3. And that's how we get this matrix here. Now we could run a loop that shows the value of each element, okay? And recall previously in our enumerate, basically we could capture the index and then the row, okay? Index and the row. And when we run this, oh, what happened? Okay, yeah, I didn't run it. Okay. We capture each of the values. So going down, right, these are the rows, right? And so A00 is equal to 1. A10 is equal to 5, right? A20 is equal to 9, right? So that's kind of how it works, right? Remember, the rows are indexed from 0, 1, and 2 because there's 3, and the columns are indexed from 0 to 3 because there's 4, okay? It takes a little while to kind of get used to that way of thinking, especially when you deal with higher dimensions. And that's kind of where the computer program comes in, right? Like we can only think in terms of maybe 2 or 3 dimensions at most. And then when it gets larger, it gets harder to manipulate. But what's great about Python is that you could write code to do this for you. So now we're going to go on to tuples. Tuples are immutable ordered sequence of elements. The individual elements could be any type. So you see we've got an empty tuple, we've got a couple of numbers in Python. Now, if we add these two, we could concatenate. Well, it's an empty set, right? So what if I did this instead? R programming language, and then yeah, see, it won't add. That's interesting. Yeah, it won't add a string. Okay, let's try it. Because they're immutable. You can't add, remember, to what it's saying. So let's try this. Yeah. Um, going back to let's go back to the empty tuple. We run it again. We could index it though, right? So new 0 is equal to 1. New 4 is equal to Python. Members, it's all the same. List and range and tuples have all the same characteristics, right? 0, 1, 2, 3, 4. So this index value is 4. New 0 to 2, 1 to 2. So sets and dictionaries we'll be talking about. A set is in Python is an unordered collection of unique elements. Sets are useful when you want to store items without duplicates and perform set operations like union and intersection. So here I do a couple of manipulations here. You could see that it's curly braced brackets. And what I do is like I add 6, right? So you add 6 here. You remove 3, right? So it removes the element 3. Remember, this doesn't use index. It actually takes the value. Here's another set. So basically 4, 5, 6, 7, set union, right? So it'd be like 1, 2, 4, 5, 6, 7. Is that right? 1, 2, 3, 4, 5. And then intersection is 4, 5, 6. Let me see. This is a little, let's see. Run it again. Union is 1, 2, 4, 5, 6, 7. Intersection is 4, 5, 6. And then the difference is 1, 2. Another thing that you could do is remove duplicates, right? So 1, 2, 3, 4, 5. We see that there's multiple 3s, multiple 1s. And if we want a unique set, we could do 1, 2, 3, 4, 5. Python dictionaries, we see like these key value pairs, right? So name and Alice, age 25, city, New York. And we print this out. We could access basically the the value, right? If we want to access the value, we put the key here, which is corresponds to Alice. And then after my dictionary country is equal to USA. We could add that. And you see that here. We could also get rid of age, right? So we pop age, which is the key value, and that disappears. And then we print all the keys, name, city, country, and then all the values, Alice, New York, and USA. And then we could update, right? Put the city, Boston, and age at age 30, which will replace these keys. So these are a couple of functions that a dictionary can do. Going on to strings, string manipulation is essential in data science because it allows for effective data cleaning, feature extraction, and transformation, especially when working with text or unstructured data. Enables tasks like text preprocessing, pattern matching, using regular expressions and feature engineering for machine learning models. You could extract insights from data sources like web scraping, user feedback, user feedback and those Amazon reviews. Those text data need to be manipulated in order for like us to do like some kind of sentiment analysis, time series data. It's useful for NLP and large language models. So it's a very useful data manipulation tool. I mean, I guess it's useful for data manipulation to understand what kind of data it is and what you can do with it. So we're going to start off with something simple. Hello world. My string, it's basically blank here. We capture the first two elements. So here you could almost say you have to plus one in order to capture two. Okay. If I was to do one, it would be blank. I'd have to go to two, right? To capture H, right? This is basically getting the last element in the string, this minus one here. And you'll find that you get the exclamation point. A common string method is to lowercase all of it. Like you see that there's two uppercase letters, H and W. So we can get the lowercase, all of it in lowercase. I mean, if we wanted to, we can also get it in all in uppercase. There's also a possibility that there might be white spaces in a string. This is sometimes a common occurrence because the data is not clean and it's stripping and stripping the white space is a common cleaning practice, okay, data cleaning practice. So it should be clean. I mean, if I say if I just to show you that it actually works, I don't want to. There's a couple of white spaces here on this. Oops. Yeah. Let me do this again. And then yeah, it'll strip this space here. We could also replace world with Python. Oh, for some reason this thing didn't. Yeah, because the reason why this space isn't here, that's a good thing to point out, is that I didn't save it in a variable. So if you don't save it in a variable, it won't carry over, right? So this will work on the original here. So I'm gonna have to do this. I could just call it my string two. And then I'll do my string two. Oh, my string two. Yep, so it works here, right? Like the white space disappeared because I carried over what I ended up doing, like stripping that white space in this variable. Um, we could split the string. I'm gonna just go back to the white space one, doesn't matter. So basically I split it Here's a F string, which is basically a way of formatting a string, like formatting it. So we have these curly braces here, name, and then it takes this variable, right? If this has to be a string in order for it to work, Alice, I mean, we could try just to prove so, but this will probably not work. Oh, it does work. So we could do a number as well, an integer as well. Okay, but you probably wouldn't want it. So that was my mistake. Oh, see, yeah, it you have to put it in a string. That's what I was originally meant. You have to put the string in quotes. But the number it's is fine if you don't, it would work. It would work fine. So here's a way of formatting it. It's this dot format name, and then you would put the string here with the empty curly brackets, right? Because it this would take the place of that. Right? This gets a little bit used to it takes a little bit getting used to. It's something that you have to see a couple of times in order to like really capture it. Sometimes some people get it right away, depending on who you are. Here's something called regular expressions, and this is pretty useful in terms of string cleaning and manipulation. I mean, there's a bunch of things that you can do um, to clean data, and this is one of them. Just an example, I mean, like here, this slash D, you can capture any digit. D plus, you could capture one or more digits. W, alphanumeric characters and letters. Slash S, white space, right? So it's like taking care of white spaces. Plus one or more repetitions, zero. I mean, star, zero or more repetitions. So I give a simple example with how to find digits in a pattern. So there are 123 apples, right? We use this match is equal to, see, this is not a good usage of variable, to be honest, because we've got this here. But in any case, we use the search, right? Because we want to search what part of the string has a number, right? So we do this pattern, right? We would put the pattern here, the regex pattern, and then we would put the text inside of this search. So if match, we print the match group, and it does match. It's 1, 2, 3. Another example is finding all, right? I have 2 apples and 10 oranges, finding all that are numbers. We get 210. I mean, let's try D. 2, 1, and 0. Yeah, I mean, because the reason why it does this is because it splits it up into a string if there's 2 numbers. The D plus is what says one or more number, right? This time we're going to look at any alphanumeric character, so that's what we want to search for. Like I have an apple. So I have an apple. It'll split this up into like each letter and put it into a string. Now, what if I put W plus? It'll keep and retain any string that has more than one value or letter. I mean, it's better to use the word letter. Okay. We could also concatenate strings, which basically means joining them. And we use this. Another way of doing this is join. Hello world, right? We put it blank, join words, and we get hello world. There's also some string checking techniques we can do, like if it starts with hello, that's false. My string, sorry, it goes back to my string. See, I'm not like I haven't been really clear on following this. It's false because of this white space. Now, if I put this here, all the way up there. That's why I got, anyway, now it should be true. And you see that it happens to be true. And this is going to be true. Oh, false. Why? Oh, because I didn't put, um, yeah, I didn't put the, I mean, now it should be true. Now it's true. So that ends strings. Now we're going to move on to object-oriented programming. So object-oriented programming, it's useful for data science because it promotes modularity, reusability, and maintainability. By organizing code into classes and objects, OOP allows data scientists to model real-world problems more naturally, create reusable components such as functions and methods, and manage complex data workflows more efficiently. This makes it easier to collaborate on large projects, debug code, and scale solutions, which are important in data science tasks that involve large data sets or complex models. So I'm going to be giving a brief overview of what each concept is. Obviously, this is a introduction, so don't worry too much. Just kind of go with what I'm saying, and at a certain point, things will click. But as of now, let's talk about these concepts. So classes define the blueprints for objects, including attributes, data, and methods. Objects are instances of classes that hold specific data and can perform methods. And then functions are defined inside a class and it operates on the data. And inheritance allows for a new class to inherit attributes and methods from an existing class. Encapsulation bundles data, attributes, and methods that manipulate data within a class, restricting access to certain parts of private access. So here we go. So this is a class object and we call it data set. Okay. And here's a constructor that you need to initialize. Okay. This is going to be part of every class object that you ever see again in your life, right? You're going to have to initialize it, construct and initialize data. Okay. Or whatever it may be. Here is a method to print basic statistics. So here's a function within the class that has a specific duty, if you will, something that it's built for a certain purpose, and it's built to produce the length of elements in the data. Here's another method, right, which is a function, and it adds new data, okay? Recall that in this constructor, we had to initialize this data here, and it's called self data. All these operations, okay, all these methods are inheriting from this constructor, right? It's taking it and it's applying whatever it's given here, and it's performing a specific duty or function within this particular function, right? So summary, add data. Mean is obviously taking the average, okay? But it has to take the average of something. It has to take the average of something here, okay? When we instantiate an object or create an object of a dataset class, what we're doing is basically we're giving it data. So we see dataset 1, 2, 3, 4, 5. Now we've added data to this class. And if I print this out, if I run this, the data summary, okay, so now that we have this my data where we've actually added data points in a list, we can now perform functions on it. If I call the function myData.summary, we're invoking this function here. If I call this function mean from my data, we're invoking this function here. And same thing with this, add data. We're invoking the function here. Okay. So that's essentially what a what object-oriented programming is useful for. You can do all sorts of things with this. Like I said, it's helpful with automation as well. Like you don't want to repeatedly code something when you could just take this class and then basically run it on data sets, right? If you have to repeatedly do certain things, each time you open up a notebook, you don't want to write these functions out, right? You're going to have a class object that's basically stored, and then you could run from this class multiple types of functions. So that's the usefulness of it. It saves time as well, right? So you put an investment in writing up this type of code, and then later on, you'll see that your life is a lot easier. So key concepts, again, to review the data set. In the class, data set defines a class to handle the data. Object MyData is an instantiation or instance of the dataset class. Method, summary, add data, and mean are methods inside the class, or I mean, like you saw functions before, functions. And then encapsulation, the data self-data is encapsulated within the classes with methods to manipulate it. Okay. Now we're going to be going on to using NumPy. And the first question that you should be asking is like, why NumPy? NumPy arrays are much faster than Python lists for large data sets, okay? And you'll see that a lot of the algorithms, machine learning algorithms, if you see the back end, a lot of them are built on NumPy, right? And the reason why these algorithms are all built on NumPy is because, you know, the speed at which these algorithms run are a factor. It's something that data scientists must consider. Like you don't want to write code that takes 10 hours when it could take 2 or 3, right? And, you know, the type of data objects or, you know, the type of arrays that you use are a factor in determining that, right? So efficiency, that's one reason. Vectorization is another. Operations on entire arrays can be done at once instead of loops, making computations faster and cleaner, right? So we saw earlier the loops, the for loops, that could take some time. NumPys actually do something called, which I mentioned, vectorization, which makes it quicker. So here we could do a couple of things. We create a 1D array, and this is a 2D array. Here we do some manipulation. Here I add a 5 to this 1D array, and then the result should be adding 5 to 1, 5 to 2, and 5 to 3, which is 6, 7, 8. Here we do element-wise addition, right? Here the catch is though, I do array 2D 0, which is the first list here. So I go 1 plus 1, 2 plus 2, 3 plus 3, which is 2, 4, 6. And then I do element-wise multiplication, which is 1 times 1, 2 times 2, 3 times 3. 1 times 4, 2 times 5, and 3 times 6, which is 4, 10, and 18. So we're going to be talking about something that's pretty important, matrix multiplication, the dot product in particular. This is pretty important in data science. I mean, a lot of the algorithms are built off of the dot product. So you'll have a deeper understanding of the algorithms by understanding matrix multiplication. It allows you to do a lot of things also in linear algebra and whatnot. It's foundational. We're going to start off with an example of like a square matrix, which is basically a 2 by 2 matrix, right? So we have this matrix here, which is 2 by 2, an array, right? And then we do this np dot ab. Okay, so we're multiplying A and B. And you see matrix A is 1, 2, 3, 4. Matrix B is 5, 6, 7, 8, and then the multiplication is 19, 22. We get 19, 22, 43, 50. Okay. I do go through the example, and I do want to show you like how these multiplications actually are carried out, because I know that like when we run things, we're not like too clear on what's actually happening in terms of the results. But so we started off with this matrix 1, 2, 3, 4, 5, 6, 7, 8. Okay. What we're doing is multiplying the row of this matrix. Okay. So let me show you 1, 2, and then we're multiplying it by the column. And that's going to get us the first element here. So we multiply 1 times 5 plus 2 times 7. We're going to get 19. Okay. If we multiply 1, 2 times this column, we do 1 times 6 plus 2 times 8 is equal to 22, because it's 16 plus 20, 16 plus 6. We would do the same thing for this. 3, 4. I'm going to just do this last one. 3 times 5 plus 4 times 7. So it's 15 plus 28 is equal to 43. And the last entry is 50. And we would have multiplied 3 times 4 times 6 times 8. So that's how it's actually working. In the background, this dot product, the idea of the dot product. I'm pretty redundant. This is a step-by-step explanation, but basically it's what I just showed you. It's calculating for each entry. Okay. And just to confirm, we'll just look at the first one. 1 times 5 plus 2 times 7 is equal to 19, which is here. 1 times 5, 2 times 7. We could also summarize the data. This is important in data science, right? Because you're going to want to understand like what your data looks like from the first go. And like summarizing it provides kind of like a little bit of a window into how your data will behave. Okay. So if I run this, we could see that the sum is 15, the mean is 3, max is 5, and min is 1. Now we could get the shape. It's 5. I could reshape these 5 rows, right? Like these 5 rows into columns. So this would denote 1 column. I'm sorry, 5 rows and 1 column. Because recall, even from the lists, we saw earlier that this would be considered a row, right, within the list. And the elements inside would be columns. It applies the same for arrays, NumPy arrays. So this would be considered 5 rows and 1 column, right? Because it has 1, 2. It has 1 element in each of these lists. 5 rows, 1 column. So data scientists, it's required that there's a lot of testing. And the random number generations, like you could create like simulated data sets, training data that you could basically test some of your theories on. This is useful when you want to replicate a data set. You could replicate a data set by, like, say, for example, um, you know that a dice that's being thrown has a constraint from rolling a 1 to a 6. You could simulate that multiple times over and get a data set of 10,000 rolls, something like that, to see if maybe you have an algorithm that could predict perfectly how a dice is run. But it's useful in that sense. It's useful that you could replicate data sets and run some of your ideas on. Now, random and NumPy has something called a random.rand, which will basically create like a data, right? Of floats between 0 and 1. And then it also has like you could create integers, random integers, right? 2 by 2 integers. And that's what it does, right? A 3 by 3, remember, uh, 3 columns, and then the lists represent the rows, right? And then a 2 by 2, 2 columns, 2 elements within a list. I mean, I hate calling it list because um, it's actually an array, but NumPy and Python, right? When you change over to array, just think of them as lists in Python, but they run much faster. That'd be a better way of thinking of it. Here's some other useful NumPy functions, like a zero array, an array of ones, like a sequence of evenly spaced values. These are useful in linear algebra, like more complicated functions, I mean, and models. Something, but it's something good to know now, because later on, if you choose to decide to pursue data science further, it's a foundational concept. Now we're going to be going on to basic pandas, and this is kind of, I would say, the workhorse for data manipulation and data analysis, right? So we've looked at general Python. We've looked at general Python ideas, right? Like lists, dictionaries, tuples, and whatnot. Then we looked at NumPy arrays, and now we finally are looking at something called pandas, right? So pandas is actually where I think beginning data scientists and even data scientists now in general will spend most of their time, right? I mean, like, because pandas is so it's so good for that. It's good for processing data much better than NumPy, because it's using NumPy, but it's a more established package. So we're going to start with something called a series. Here we have a 0 column, 1, 2, 3, 4, pretty simple. Here we're creating a data frame. We have this column here, name, and then this other column, age. Notice that there's a colon, and then afterwards there's a list. Okay. And then we do this data frame function to convert it into a data frame. Now we could change this index 0, 1, 2 to person 1, 2, 3 by doing this. The reason why I'm doing this person 1, 2, 3, it's probably, you don't have to do it, but it's done because it could be easier to retrieve the value. You're not going to necessarily want to think in terms of numerical index values. You might want to think of it in terms of actually like labels. So the second thing that we do, like after, say, we've curated data set or read in a data set, we would have to explore it. And here we basically look at head, tail, info, describe, shape, and columns. Okay, so head is basically like maybe the first 5 rows. Tail is the last 5 rows of the data frame. Info is like the data types, right? Non-null counts. Describe is descriptive stats, min, max, standard deviation, quartiles. I mean, we saw the NumPy array where it gave some of the descriptive stats, but this is more, what's the word? High level, because it's got a built-in function that'll do all this, right? We don't have to do NP mean, NP standard deviation, NP max, NP. We'd have to write 4 of those functions to capture all 4 of these. We're here describe, we just capture all of it, right? And that's the distribution of a data set, right? So usually, when we look at a data, I mean, eventually, hopefully you'll end up looking at this. We could have some kind of bell curve. We'll see this later. Here's a max value, here's a min value, here's the mean value, something like along those lines, okay? But this one line of code will capture all 4 of what NumPy was doing, all 4 things, just in one line of code. And then the shape is the dimensions, right? The rows and the columns. And the columns is the columns of the data set. So here I print out the first 3 values, see the shape, just 3 by 2, which is, remember the order of that, rows and columns. There's 2 columns here, 3 rows. Now we could print out the columns itself, name, age. This is useful. I mean, here we're working with a small data set, but say, for example, if you got 100 columns and you don't know what they are in the data set, instead of reading through all 100 on the spreadsheet or in your printout, you could just do df columns and see all the columns that you have. Okay. It's a good way of accounting for columns too, the columns that should be in there. Maybe there's some that are not in there that should be, whatnot. So it's a good check. Here's a summary of info. Here you're going to see something like what kind of data type it is. And at times you're going to need to, do some conversions, right? Like if age I mean, if there's some value, I didn't include date in here to do date manipulation, but dates have something like a datetime object, and you're going to have to, they're going to be seen as this, but you have to convert it into a date, right? So this info here is kind of giving you a rundown of what the variables, 1, are, and 2, what's their data type. Okay. Again, it's another way of accounting, like what kind of manipulations you're going to have to do later on if some of them need to be changed. So here's what I was saying about the descriptive statistics. You got it all here. You get the median, the 25th percentile, 75th percentile, the max, mean, and then also the number of observations. Here's another thing that might be useful. Like you could count how many rows there are, value counts. I mean, if I wanted to do it for a separate value, you could do the same thing. It's basically seeing kind of the breakdown of age, right? Here we have such a simple example, but if this occurred twice, it would be 2, whatnot. And again, this would show you kind of the kind of the behavior of your data set. If it's evenly or, if there's more values in one. I mean, like if you had like a data set that had 25, 30, you'd run some value count and then it had like 1, 1, and then you see the 35, there's 100. You could see that that particular data set is biased towards the age of people in 100, right? So if I had 1, 1, 100 instead, you can see that this would dominate the data set. Now that could be a problem, or it could be something you want, or you might want to just drop these values, right? And we'll see that. We'll see how we can do that later. So here we could find the column by just bracketing it and then the name of the column. Say I wanted people that are older than 30. What I would do is I would do the DF age greater than 30, because that's the condition. Is that true? And then if that is true, then we could extract that from our data frame. Right? So that's it's like a nested, it's a nested set of values, right? Because the first thing you want to do is create the condition. I want everybody whose age is greater than 30. And then from there, that's your like what we call a subset, right? And that subset is being taken from the original data frame. So if it meets this condition, then that's what will end up being the result. It's taking it from this data frame. So this loc method or command retrieves basically the index values. Okay, so if I wanted from the original data set, person one and person two, I could do df.loc person one to person two, and it'll run it, and it'll capture Alice and Bob. Okay. Now I can use df.iloc too, and instead of person one and person two, I could use 0 to 2. So remember that I changed um, the index values to those labels, person one, person two, person three. But originally it's actually 0, 1, 2. I just want to make that point. And remember, it's going to capture person one, 2 at 0 to 2. Now, if I did 3, it would capture everybody. Another important cleaning technique is to handle missing values. Okay, so in your data set, you might have missing values. What are you going to do about it? That's something that you have to worry about. So if we say, are there any missing values? df is NA, we could use this command, and we see that there's none. We could also count how many by isNull.sum. It'll give you the count of how many missing values there are for each variable, and there are none. That data set was perfect, right? In most cases, we're not going to get that. Now let's look at another example here, where we get a couple of NaNs here, missing values. We want to fill these NaNs with 0. And those would be populated with 0, those missing entries. If I said 10, it would be populated with 10. So, 0 or 10 or 20, I mean, you could get information, say, outside of a data set and say, hey, you know what? Bob's real age is 30. Then you would do that, right? Or, Eva's age is 20. You would fill that. Okay, so if I wanted to just fill Bob's name, No, it doesn't work. Why not? Oh yeah, yeah, yeah. Oh, sorry, yeah, yeah. You can't do that. You have to do. I'm wondering if you could do this. Yeah, it's not going to work. I mean, it's only by column. So that's an important point to make, that it's only by column. Yeah. So it's going to do 10, 10. There's another way of doing it. You're going to have to kind of parse the data set and then apply this to each parsed data set, but it's a little bit beyond the scope of what I'm trying to show you. But it's a fill NA, basically fills a missing value. Now I want to rename the column from age to years. And I would do so by doing rename columns equals the bracket age colon years. And we could see that it's changed to years. Okay. Here's another function to fill missing values, this time by using apply. So I create this function, and this is probably what you would have to do for what I was showing earlier. But if column D type is equal to float or is equal to the integer, then fill it with the mean, right? If it's a gender, fill it with male. So you could see that when I said fill in a 10 here, that it was indiscriminate in terms of columns, and we saw that the 10 got filled in here. Okay, that would be a mistake. Okay, so this function kind of takes care of that, right? So if it's equal to a float or an integer, which is a number, then we fill it with the mean. If it's equal to gender, which is a string, then we fill it with the string male. And this apply, we use the data frame, apply that function. Axis is equal to 0 is for every column. If it was axis is equal to 1, it would be every row. But most of the time, you would want to get it where you're applying this function on every column. And we see that we get it filled out. That's male. Yep. Yeah. Taking the average is not a bad idea from the data set. I mean, there's more sophisticated ways of filling in missing values, but average is not a bad idea. Or the median, for that matter. Here's basically transforming the years. We see that this is a string. I mean, not a string, I'm sorry, a float, where it goes to certain decimal places, and we're not concerned with that, right? So I want to transform it into just a pure integer. And that's what we do. And it turns 25, 25, 30. We could sort the data by years, by age, years. I mean, I should have probably kept it at age, but by years, and then 22, 25. Recall, I didn't carry the integer here, so you have to store it in this variable. I'll do it right now just to keep everything we've done changed. And then what? Let's just keep it. I don't know. I'm not gonna wait. Yeah, something wrong. Oh yeah, I know why, because it just didn't carry. Let's just do it by age. So, sorry about that. So here it is. I sort again by years, 22. I'm just going to keep this decimal, but you have to carry it. You have to save it and then carry it in order for it to be an integer. And then we're going to make this ascending. I mean, descending. So it goes from the oldest to the latest. I mean, the oldest to earliest. And that's going to matter at times, right? Say you want something like, you're a sales guy, you want to see what states had the most sales from the highest to lowest. You would do something like this, right? And the data comes in all messy, whatever. Here's another example. I've got a bunch of NANs and I've got duplicate Bobs, right? I mean, Bob has like multiple entries. Um, a group by is a function that we use to kind of summarize data in a way that's useful. So here, I mean, we've got 10 entries, but say if there was a million and there were about 10,000 Bob entries, right, all over the place, right? Group buys could do something like, and I want to know something about Bob. I want to see his average salary, you know, throughout his career or something like along those lines, right? We could aggregate that information for Bob, right? So like, let's say if I want to group by age, um, group by name, and their gender and their account. Okay. So I could see how many times this is probably not a good variable name. Group by gender. Uh, so I'm going to group by gender. How many times does Alice appear? Right? How many times does Bob appear? Right? How many times does Charlie appear? See here, you see Charlie is a good example of what would have happened. Charlie appears only once, his gender, right? Because we're seeing the count of gender, right? How many times is it appearing um, for Charlie? I mean, each of these, what happens is that each of them are occurring twice, right? Say for Eva too. Well, actually, Eva, no. Eva works out because Eva has two females, two Fs, right? So we're counting how many times are being counted as female. Here's a TV sales example, which will probably be a little bit more clear. Say Samsung TV is selling to China, US, and Europe. Okay, and you've got all this data points of like how many units they've sold, right, for each month, right? I mean, January, they're all aggregated up to January. And you get all this data here and you're seeing the sales. Like, what what if we wanted to know how much sales were made for each country? We could do DF group by country, and then we do a bracket sales dot sum. This dot reset index makes it all flat columns. I recommend doing this. And then we see how many sales were made in each country. Okay, and obviously the US is the largest. I could have sorted this from largest to smallest. How about sales by month? So here, instead of name, I mean country, we would do month, but we would still keep sales here, right? And then dot sum reset index for, and it's a good idea to sort it by month here. January is 3,700, 4,000, 3,850. Another thing that we should be doing is possibly merging data frames. So one data frame might have a particular set of information and another data frame might have another set of information. and we want to get like a holistic picture, say, of somebody, right? So I do this merging data frames, DF1 and DF2, where we've got Alice and Bob, they've got IDs, we've got their names, but we want their age. And that gives us a better profile as to who these people are. I mean, this would be important, for example, if you want to target ads or advertisements or I just said ads, or anything like emails, right? That kind of information could be useful because you could tailor your marketing towards the demographic that you're interested in. So here what I do is basically do create these two data frames and then use this thing called merge. And then we merge it on ID because the ID here is what connects these two data frames. We can't connect it by name and age, but we can connect it by the common identifiers in the table. Oops. Alice, Bob, age, common ID, and then we merge and we get that table. Here's another example. This time we're reshaping data. Like you're gonna find while you're doing some data cleaning or data processing that you're gonna have to do this at times. I've got this data set with soup, smoothie, the date that it was sold and whatnot. Now we want to transform these values to be out in the columns, right? It's called from long to wide, where we have soup, smoothie, and flatbread as the columns. Now, in order to do that, we would use something called a pivot, right? Where these values will end up being the column values, okay? What we would do is use something called, like I was mentioning, pivot. We'd index it by date. Columns is equal to collection, right? Because this is what we want as the new columns. And then the values would be the unit sold. We reset index, rename axis none, axis is equal to 1, okay? I just want to show, I filled the missing values in with 1,000. And the reason why I did that is because it's not capturing, like it's a small data set, right? So there's going to be some missings that occur. But I don't want you to pay attention to that. I want you to pay attention to the fact that the manipulation is occurring where it's going from a long to a wide. Now there's a thing called wide to long, okay? We've got this here where we've got January sales, February sales, and March sales, right? Now we want to get this on inside of a column called month. So we would take this DF wide, ID variables is equal to product, var name is equal to month, value name is equal to units sold. Okay. So this here would turn into columns. It went from rows to columns. So this is what this melt would do. Right? ID vars is equal to product, variable name is equal to month. You do variable name, there is no variable name called month, but that's what you would do. And then value name is equal to units sold. Another operation that's pretty important is concatenation. Now here you could see that there are two separate data sets, but they're symmetric. They've both got two columns, right? This is denoted by as an index value. And then when you stack it or concatenate it, whatever term you prefer, you'll get this bigger data set. So let's see what would happen. So we've got this DF1, product unit sold, DF2 product unit sold, and we would stack it. So it would be 250, 200, 450, 300, 150. And that's what occurs. You could also do it horizontally, right? Because since it's a 2 by 2, but it wouldn't make any sense, right? Like if we stack it on top of each other, then we could we stack it by row, right? Here, if we do axis is equal to 1, we're adding it by column wise. So you see this product unit sold, product unit sold. This probably doesn't make any sense. It's not something you would want to do, but I want to show you, okay, when you're stacking, okay, the mistake you might make is this, is that you might stack it horizontally you might stack it vertically as opposed to horizontally, okay? Um, so make sure when you stack something that you know what dimensions you want it in, okay? Because this will still remain two columns. It's a 2 by 2, right? 2 rows, 2 columns, right? But it'll still remain 2 columns, okay? Here, you're going to end up having 4 columns. And also, besides the fact, it's going to be redundant. The columns are going to be redundant. The values won't be, but the columns will be. And there is no real use case for this. So making these kind of mistakes is actually kind of useful because you kind of see examples that you want to avoid, really bad things that you might want to avoid. Now we're going to be talking about data visualization, and this is also very foundational to data science because it helps communicate complex data insights into an intuitive and accessible way. By transforming raw data into visual formats like charts, graphs, and heat maps, data visualizations allow patterns, trends, and outliers to be easily identified, enabling better decision-making and more effective storytelling. It's more accessible to non-experts, and it helps convey results in a clear and persuasive way. Not everybody's going to be able to understand formulas. Not everybody's going to be able to understand, complex models, but visualizations could kind of bridge that misunderstanding or misperception, okay? Because as a data scientist, at some point you'll be building these models, you'll understand it, but that's not enough. Your audience has to understand it. Your audience has to understand what you've done. Your audience has to understand what kind of insight you've garnered from your analysis. Now, we looked at pandas and we looked at this value counts function. I do want to make the point that there is a plot here, and we could plot bar. I'm tossing a coin, random choice, results 100 simulations of a coin, and I could plot it. So that's pretty useful to know. This plot behind value counts. Here's a typical line plot. This is good for showing sales growth, maybe profitability, up for like trading strategies if you're in finance. Here's a scatter plot, which shows basically like relationships, right? I mean, here it's tends to descend. You've got one value here that's misbehaving. Here's another bar chart. You're going to always have to have a title, an X label, a Y label, right? And then use this plot show. You're going to see that that's common between what we see in the X label, a title, X label, Y label, and then a plot show. So that's the common syntax between all these plots. Here's a histogram of a normal distribution, which we'll be seeing shortly, or we'll be talking about shortly. Here are box plots, a pie chart, and a heat map. Now, what's good about a box plot? A box plot is good at like possibly capturing outliers, right? And you see these dots outside of these quartiles. Okay, remember we saw the mean, the 25th percentile, 75th percentile, max, min. A box plot is basically that, except shown in a diagram. And we've got multiple for each one, A, B. Yeah. Here's a pie chart, the breakdown. I mean, this is useful for say for example, in our earlier explanation, we had sales for China, Europe, and the US. Most of the sales are in the US, and 50% of the sales in the US, 30% China, 20% Europe, that kind of breakdown. Here's a heat map, which is basically a correlation plot, seeing like how close things are related. If we look at the 1 and the 4, if we look at 1 and 4, for example, we see this yellow area. And the more yellow it is, the higher correlated it is. If we see 3 and 1, we see this purple. It's not, the correlation doesn't work, right? So how is it related? If it's related, it gets more yellow. If it's more closely related, that's the way to read it. So now we're going to be talking about statistics, and statistics is foundational to data science because it provides the tools to analyze, interpret, and draw conclusions from data. It enables data scientists to identify patterns, test hypotheses, quantify uncertainty, and make predictions. Through statistical methods such as regression, hypothesis testing, and model evaluation, data scientists can ensure that their findings are reliable and actionable, ultimately driving informed decision-making and robust data-driven insights. We'll be looking at company sales data and demonstrate statistical ideas that will be of use in analyzing the company's performance. Now, recall that we've seen this a number of times, some of the basic statistics. I use NP mean. I should have used, well, here, the reason why I'm doing NP mean, right, is that I'm creating what we call a synthetic data set with a list, okay? So it's more useful to do the NumPy instead of the pandas because it won't work. It simply won't work because it's not a data frame. So we capture some of the statistics, average monthly sales, median monthly sales, standard deviation, the range, 25th, 75th percentile. There's something called Bayes' theorem that's useful in data science. Here we could read this statement as the probability of A given B is equal to the probability of A intersecting B divided by probability of B. Probability, this could be called the posterior probability. A and B is the joint probability. Probability of B given A is the likelihood, right? I'm not too concerned about this. The probability of A is the prior probability, and probability B is the marginal. So say if the probability of a customer buying a product is 0.3, and then the conditional probability that he subscribes given that he buys is 0.5, right? And we want to find the probability they buy and subscribe to an email list. It would be probability of buy times the probability of subscribe given that he buys, right? So here is the multiplication, right? Probability of B times probability of A given B, which is probability of the buy, 0.3, times the probability of A given B, right? We're given these two pieces of information so that we could fill in this, okay? So the probability that customer buys is 0.3, and the probability that the customer buys and subscribes is 0.15. So here's some statistical distributions that are pretty useful. Say we want to find out the delivery times in minutes for these like particular products. We could use a normal distribution. And then we could use the Poisson distribution for the number of website visitors per hour. So now you could see that there is a distinction. This is called a continuous distribution, and this is called a discrete distribution. In a continuous distribution, basically the values are numerical, right? And it's continuous, okay? In a discrete distribution, they're basically counts, okay? They're counts and they're not continuous. Something could occur where a website visitor, 100, come to your website in 1 hour. Then the second hour it could be 0. Third hour it could be 100, 200. It's not a continuous thing, right? So we see this density where we could model it, right? This probability density function, and then we see the actual values. Here we just see the values, okay? It measures basically counts and how many, in this specific example, I think it could, okay, so let me just experiment with this for a second. Yeah, I mean, it could model a density, so I retract that, but it's basically measuring counts, how many times things are coming in. Okay. Here's a binomial distribution campaign, the number of emails sent being 1,000, and then the probability of an email being clicked is 10%. So we want a probability that exactly 120 people click. Here we could put in these parameters, the number of trials, which is 1,000, P, which is 0.1, and K, which is 120. And this has come from SkyPy.stats binom. And if we do something like this, we click on 120 clicks, and then probably out of 120 possible clicks is 0.0047, right? The probability of that occurring out of 1,000. So that's a usefulness of statistical distributions. It kind of gives us the tools to analyze the behavior of wait times, right? Time is a continuous variable, but arrival of people is a discrete variable. these kind of things, okay? An A and B test is whether marketing affects, testing whether marketing affects spending, right? It's a test of like seeing how your customer behaves based on some type of stimulus that you provide. And then how to measure whether marketing affects spending is to look at the T statistic and P value. So what exactly is a T statistic? Imagine you're testing whether two things are really different or if the difference you're seeing might just be some type of random chance. The T statistic is basically a number that tells you how big that difference is compared to how much random noise or variability there is, right? An easy way to understand this is that the difference is big compared to noise, so there might be a real effect. A small T statistic, the difference is small, so there could be due to random chance. Now, in our marketing example, will marketing affect spending? Right? That's kind of like what we're trying to figure out. If it's a big T value, then it's not by random chance that the marketing dollars we spend actually affect spending. Okay. If it's smaller, then it might be just random and there might not be a point to it, the marketing. So what's a P value? Once you have a T statistic, you ask, how likely is it to get a T statistic this big just by random chance if there's really no difference? That probability is the P value. So low P value is very unlikely to happen by chance. Evidence there's a real effect, okay? There's causality. And then a high P value could easily happen by chance, and there's no strong evidence for a real difference. So the average spend before a marketing campaign is these values, and then after campaign, it's these set of values, right? And if I run this stats.ttest IND between two independent samples of scores, right? Before campaign and after campaign, we get a T statistic of negative 4.72 and a P value of 0.0014. So this is probably not happening by chance, that there is a profound effect of the marketing on the on the spend afterwards. So we're going to be talking about covariance and correlation. And covariance is how two things move together. It tells you whether two variables move in the same direction. So positive covariance, when one goes up, the other tends to go down. Negative covariance, when one goes up, the other tends to go down. Near zero, there's no clear pattern, but covariance doesn't tell you how strong the relationship is or gives you a standardized number. So it's a number that you shouldn't really look at too closely. Correlation is something that you should be looking at a little bit more closely in terms of the number. And it's a strength and direction on a standard scale, right? So there's a standardized scale for it. And it's not the same as covariance, but it standardizes the result. For those that are more mathematically inclined, it's basically if two variables, X and Y, correlation is basically the covariance of X and Y divided by sigma X, sigma Y, which is the standard deviation of X times the standard deviation of Y. And it'll always give a number between -1 and 1. 1 being a positive, perfect relationship, -1 being a negative relationship, and then 0 being there's no relationship, okay? Another thing that I want to point out, I mean, for you that are not familiar with statistics, is that perfect correlation doesn't necessarily mean causation, okay? Especially in complex phenomena, there could be a number of reasons why something is occurring. And you don't want to, when you gather data, see something and automatically make the assumption if there's a high correlation that it happens to be causal. Okay. As an example, say like if we were, I mean, this is a little bit of a ridiculous example, but it illustrates the point. Say if we have stock market data and we collect data on basically whether the moon turns, whether there's a full moon, and we collect each day, and it happens to be that when there's a full moon, the stock price goes up, or the stock market goes up. Now from the data, we collect a correlation score of like 1 or something high, 0.95. But we know intuitively that that is pretty ridiculous, right? So when we look at statistics, we have to look at in context of other factors. And we have to use also some of our common sense reasoning into whether that relationship is meaningful or it's just by accident, even if the correlation is 1. So that being said, we're going to go into our example, and we're talking about the advertising budget and sales revenue. And we see there's this correlation between of 0.98. I mean, obviously the data has been constructed to give nice, clean results. In the real world, it probably wouldn't work out that way. Now we've got multiple variables: advertising budget, sales revenue, product price, and customer satisfaction. And I want to build a correlation matrix. Okay, so we saw that DF here, the data frame, has a function .core and .co, right? The correlation and the covariance. It also gives us a means, right? We also have a way with something called SNS, Seaborn, and Matplotlib to build a correlation matrix from these 4 variables: product price, sales revenue, and customer satisfaction. Okay. We do that and we run it, right? CMAP is equal to cool, warm. We do some formatting. C bar is equal to true. And we get these values. Now, the way to interpret it is like we saw one of these graphs earlier, but there was no specific labels to them. But say sales revenue and product price is highly correlated, right? Product price and advertising budget are highly correlated. I mean, but that doesn't make sense, right? So we're looking at a variables, and basically what a correlation matrix does, it helps us see things and their relationships to one another. Regression analysis is a form of predictive modeling, and it investigates the relationship between a dependent variable and an independent variable. Okay, so this is the formula here for those that are a bit more mathematically inclined. But y is the target variable, beta naught is a intercept, beta 1 is a coefficient, x is the actual variable, and this error term is noise. Okay. So is there a relationship between advertising budget and sales revenue? I already run this, but we get this here, right? And this is coming from the model, the package stats models. Okay. It's a lot different from standard machine learning models because this is more inference based. Okay. Now we see this, and remember the t statistic and the p value that we were talking about earlier. We saw that if we have a high t statistic, which we do, and a low p value, which we do, this will, advertising budget, which we have a coefficient of 9, will affect Y, which will affect, wait, let me see 1 second. Sales revenue. Okay. So for every, like the way to interpret this is like for every 9 units, okay, it'll affect the sales revenue. Okay. That's all I think you should be looking at, especially when you start out. And also this number here, how good the model fits, which is 0.976, which is really good. Okay. In this case. But the thing that you should be thinking about is basically the values here. Does advertising have a positive effect? Is this meaningful? Okay. This stuff is a little bit more advanced. You shouldn't concern yourself about this, but these are the statistics that I would be concerned about. Regression modeling is the workhorse for machine learning, so it's important to know. And this is basically an immersion type course, so you're going to get working knowledge of all these ideas. Now we're on to basic machine learning skills that you will need. Machine learning is foundational to data science because it enables models to automatically learn from data, identify patterns, and make predictions without explicit programming. It automates complex tasks, handles large and diverse data sets efficiently, and improves over time as more data is processed. Machine learning provides a versatile range of tools from regression and classification to clustering and dimensionality reduction, making it essential for predictive analytics, decision-making, and real-world applications across industries. So we're going to load first some machine learning packages. We're going to have to load NumPy and Pandas, okay? And then from scikit-learn, train test split, linear regression, mean squared error, and accuracy score. So these metrics here show you how well a linear regression performs, okay? The model. And that's what we're going to be looking at. Here we're going to be loading the data. Creating some data. Size, square feet, and then the price of a house. We implement this train test split here after we split the data into X and Y. So we know that what we're going to look for is basically the price of the house is what we're trying to predict based on how much square feet we have. And this will have this X train, X test, Y train, Y test, okay? What we're going to fit the model on is the Y train and the X train. And then we're going to try to predict Y test. Yeah, Y test and see how well it does. So I run this, I split the data. I see like how X train looks like, our training set. We initialize the variable, call it model, then we fit the training data, right? We're trying to predict how well why what how we want to we want to show how well our predictions compare to Y test after we predict X test, okay? Y predictions, okay? What happened? Oh, I didn't run it. So we get that. We get that. I run this. Okay. Now let's look at how well our, so MSE is mean squared error. It's pretty low, 3.6, right? It's close to zero. So here we did a continuous model, okay? Like we did a regression, okay? Now we're like for a continuous value, right? So like let's look at our Y predictions. See, it's 149 and 157, right? Because we're interested in the price of the house, right? And those are in hundreds of thousands of dollars, okay, which is a continuous variable. It's called a continuous variable. Discrete variable classifications, okay, they take on discrete variables or Boolean values. I don't know if you recall from earlier, we talked about Boolean values, 0 or 1, true or false, yes or no, um, cat or dog, right? That would be fall into like what a classification model is, okay? Here, I'm going to make a fake data set here, and then I'm going to use a decision tree classifier and then do an accuracy score. The accuracy, again, so we do the same thing earlier, right? Where we split it up into X train. I want to do this. X train, Y train. We predicted on what X test, right? To get predictions. And then we compare it to Y test because this is the data set we hold out to see how well our predictions compare, okay? So when we do that, we initialize the classifier, we fit it on the training and the Y train, and then we predict it on the test, X test. And then we compare our predictions to the Y test, right? We're interested in the target variable and seeing how well our model performs on that. And it does pretty well. We get a 0.97. Obviously, the data set is it's lean towards success, okay? And just to show you what a classification variable looks like, I run this. See, it's 0, 1, 0. It's a bunch of zeros and ones, okay? I mean, you could say it as like yes, no, whatever. I mean, I made up a data set here, but to illustrate, I wanted to illustrate the point that these are different, right? It's constrained to like 0 and 1, whereas the housing values, it was a range of values, right? There was like we could run um, these summary statistics. We couldn't do it on this, right? We could do uh, a value counts on this, right? Um, what So we do something like this. Let me see if this works. Yeah, it works. We could see how many times the zeros and ones up here. So there's 0 ones and zeros, 15 zeros and 15 ones, right? So in order to evaluate whether or not we correctly classified a value, right? So if it's a 0 and we predicted a 0, that would be correct. If it's a 0, but we predicted a 1, that would be incorrect. If it's a 1 and we predicted a 0, that would be incorrect. If we have a 1 and we predicted a 1, that would be correct. So that's kind of the way to look at it. Now, that 1 and 0, you could replace it with labels like yes or no, true, false, or whatnot. Okay. A way to evaluate how well your model performed is to use something called a confusion matrix. Okay. And we could see in this matrix, okay, the basic idea being wait 1 second. So here, like as I was mentioning, is the confusion matrix, okay? In order to interpret this, we would have to look at it from the vertical axes and also the horizontal axes. On the vertical axes are the actual values, and on the horizontal axes are the predicted values. Now, if the actual value is a 1, and then the predicted value is a 0, okay, that would be considered a misclassification, okay? If it's a 1 and a 1, that would be considered a correct classification. If it's a 0 and it's predicted as a 0, that would be correct at 15. Okay. And we see that for the most part, it's incorrect. It's correct, right? 1, 1, 0, 0 at 15. We do have an issue though here, where the actual value is 0, but we predicted a 1, and then we get an error here. Okay. You want to minimize these off diagonals and try to optimize and maximize this diagonal value, okay? So the goal would be to have these as small as possible. There's also something called a classification report where we get a number of values here. We saw the accuracy score, which is the difference, which is comparing the predicted values and the actual values and seeing how close they are. But then we get a bunch of other ones, right? We've got precision, recall, F1 score, and support. Precision, high precision means that the model is making few false positive errors, right? Predicting a negative as a positive, right? So predicting a 1 as a 0 or a 0 as a 1, right? Recall is high. Recall means that the model is successfully identifying most of the actual positives, okay? Low recall means that the model is missing many true positives. Okay, so we've got a perfect recall here. We've got 0.94 for 0, right? Because here, when 0 is an actual, we predicted it as a 1. The F1 score, a high F1 score, indicates that both precision and recall are balanced and high. A low F1 score indicates that either precision or recall are performing poorly. Support, this tells us how many instances of each class there were in the test set. If one class has a much higher support than another, this can skew the metrics of precision and recall. And accuracy, this is the overall measure of correctness, but it's less useful in cases of imbalanced classes. For example, if 95% of the sample belongs to one class and the model can only predict that class and still have 95% accuracy, but it wouldn't be a good classifier. So if there's like 100 dogs and 10 cats and you get a 95% accuracy of getting dogs. It's just not a good accuracy. It's not a good measure because of the fact that most of your data set is filled with dogs, right? Instead of cats. Cross-validation, this is a good technique to know as well. It's a technique using to assess the performance of a machine learning model by testing it on different subsets of data to avoid overfitting. It measures how well the model generalizes to an independent data set, how accurately it will perform on unseen data. In a typical k-fold cross-validation, the data set is split into k subsets or folds. The model is trained on k-1 folds and tested on the remaining fold. The process is repeated k times, each time with a different fold as the test set. The performance measures such as accuracy, precision, recall, or error rate are averaged across all k iterations to get a more robust estimate of the model's generalization ability. So it takes basically one fold and runs the model on it. I'm sorry, it takes it splits the data into five folds, okay? The ones in the green are the training data. So it'll run the model on this and then predict on this test set. So it'll hold out one test set, right? And it'll train it on fold two here, split three, split four, split five, right? So the blue is the test data, okay? So if I run something like this, we could use something called cross-val score from scikit-learn's model selection. And we could see that the individual scores are here, right? So we have five folds, right? 1, 2, 3, 4, 5, right? So this performs at 69%, 71%, 78, 85, 84, and the average is 78%. So that's the idea of cross-validation. And I've given you some Python code to run it. The linear regression here is where you place it inside. You have to place it inside this cross-val score function. Put the training, the target, and the number of cross-validations, okay? And then the scores. You're going to see later on that NumPy is very useful and it interacts well with scikit-learn for some of the things that you're going to need to do, okay? This is our final section, and we'll be covering something called unsupervised learning. Now, unsupervised learning, there's no target variable y here. We're just working with x. We're trying to find structure in the data, okay? So say, for example, we're given a data set and we want to cluster based on several demographic variables, like who's making the most sales, okay? And we have, age, zip code, and all these other things. Zip code, um, whether you're male or female. We've got a host of characteristics. Like, who are the people that tend to buy our goods, right? Like, and we could create like clusters based on this, right? Like which people are on the average, like hanging out together and online or whatnot, right? We could segment different parts of the population to build these target campaigns, right? Sales campaigns towards, right? And we could target them based on a bunch of these attributes that I just mentioned. So we would do something like this. We could use something called k-means from scikit-learn cluster. And I generate synthetic data here, but I apply it and I want three groups, okay? And I fit it, I get the cluster centers, okay? So if I was talking about like the age, the zip code, um, the sex of the person, um, how much they spend per year, how much they make per year. We could get these cluster centers of people that are basically the archetypes of that particular group, right? The ideal person. Okay. And then we create labels. This is the generated data. So, like I said, I mean, we could look at these people, we could segment, say like customers into like three groups. And they have distinct characteristics, whatnot, right? The algorithm will bring us to this. It'll give us these cluster, it'll give us these clusters, okay? These cluster centers. And in these cluster centers, the cluster center represents kind of the ideal person, okay, within these groups. So this is basically unsupervised learning in a very quick but descriptive way, right? And that ends it. Thank you very much for watching. I hope you pursue data science. This has been an immersion course. I'm extremely happy that you joined, and thank you again, and good luck.